Today is going to be, when I set up this order, go through teaching a segment, giving you the homework problems for a segment, today is pretty review question heavy, and knowing that next week during the testing time, we're going to have a couple days. The first day is going to be a full period, but a couple of those are going to be a little bit shortened because of testing. So I may press on today in lecture, after we go through the problems. Go ahead and press ahead in Dalton's law of partial pressures, because it's going to be to your advantage to have a little bit more time with this end of the chapter. The latter part of the module has a lot more questions on the exam. Also, if you just think about it, like the EPPs and stuff, we haven't even gotten to some of those. So want to make sure you've got more time in that concept. And today, after we do the review of the questions, I'll just roll right into Dalton's, actually mole fractions, and another way of using Dalton's law of partial pressures. So even though this may be amended even after today, does anybody still lack the current plan? Anybody still need one? You received one of these earlier, but I updated it on the 18th. So if you need the update, I'll have it up here. I'll keep one for myself because, frankly, I don't remember day to day exactly what we're supposed to do necessarily. But let's go ahead and take a look at the homework problems you had for last night. That's back in review questions 5 through 9. Let's start with that. Okay. So first, as I mentioned before, when you get into the properties of an ideal gas, generally speaking, you're going to be asked to identify what those properties of an ideal gas are, just to know them. Your actual implementation of the concept of ideal gases, or non-ideal gases, more specifically, will come later in your chemistry careers. So at this level, it's just really a matter of knowing what are the characteristics of an ideal gas. And there's 3 of them, 3 characteristics. So what are those? If you can, without looking at your book or your notes. The 3 different characteristics of an ideal gas. Let me give you some visual hints, maybe. Okay, so from the lecture, what does that remind you of? It's a question about volume, right? Or a statement about volume, actually. That the molecules that make up the gas are small relative to the volume. I said this would not be an ideal gas, where you've got a molecule, you've got a container that's so small that it's a molecular size container, and the container holds a single molecule of gas. That gas cannot act ideally. Right? The volume of the container has to be many times bigger, has to be much bigger than the volume of the gas. Okay. The second characteristic had to do with the nature of the molecules with one another. So an ideal gas behaves in what way?
Don't they go so far apart that there's no attraction or repulsion?
Right, exactly. That's the second characteristic. That there's enough space, they're far enough apart, that there is not a physical, actually it's due to forces, due to charges, but there's no attraction or repulsion between the molecules. Okay? And the third one has to do with the elasticity. So there's a conservation of energy that's taking place. As a molecule hits another molecule, or as a molecule hits a sidewall of the container, it reflects off and there's no loss of energy. It's an elastic rebound takes place. Okay, so those are the 3 characteristics of a gas, of an ideal gas. Generally speaking, in virtually every problem we deal with, other than describe what would make it not ideal, the gases we deal with, the problems we deal with, are with gases that behave ideally. The only statement you really need to know about ideal gases is if it violates any one of those 3 characteristics, you cannot use the formulas for gases that we're learning in this module. And so every problem you're given, unless they said something weird like, is in a container that's so small that only 2 molecules can fit. Okay, you're going to say, no, that gas can't act ideally. Other than that, your problems will be with gases that are acting ideally. All right. So, the properties of an ideal gas, the conditions of an ideal gas, and what do they behave ideally? Those are both kind of balled up together, right? Their properties, their conditions, and what is STP? Standard temperature and pressure.
Sorry, temperature is like 273 Kelvin, and I think is it pressure that's 118?
1 atmosphere. 1 atmosphere and 273 Kelvin, which is basically 0 degrees Celsius, freezing point of water. So when it says gases behave ideally, just before that, when do they behave ideally? They behave ideally at or around STP. When the temperature is at or above, what it says is near or above, not at, near or above standard temperature, and the pressure is near or below standard pressure, gases will behave ideally. Okay, so it meets those 3 characteristics and it behaves in that zone. And just in your own mind, when they say near doesn't mean like, are we talking a 1/10 of a degree, 1 degree? They're talking more in the range that we're used to, the range in which we live. So again, many of the practical examples you hear, you know, a chemist is in a lab and collects gas over water. Well, you know what? That's going to be in that temperature range and in that pressure range. It's going to meet those conditions. So standard temperature and pressure, STP, is 273 Kelvin, which is extremely close to 0 degrees Celsius, which we call the freezing point of pure water, and standard pressure of 1 atmosphere, also known as 760 torr, 760 millimeters of mercury, and 101.3 kilopascals, 1 atmosphere. Okay. Number 8, a little bit more concept here. 2 steel containers of equal volume contain 2 different gases at the same temperature. The first container holds 1.3 moles of nitrogen gas. The second contains 1.3 moles of SO3 gas. Okay. Compare the pressures. What are the pressures going to be? How do they compare to one another? At the same temperature, same volume, same number of moles of both gases. Is it surprising that the pressures are the same? Remember, the pressure does not have to do with the characteristics of the gas. It's not the gas itself that determines what the pressure is going to be. The pressure is determined by the amount of the gas. The fact that there's 1.3 moles of both, you've got the same size container, same pressure, same number of moles, you get the same pressure. They're all the same. If you had a different number of moles, you can't do that problem yet, but we will very shortly be able to figure out what the difference would be. Okay? And the point being driven home there again is that the pressure of that gas is not determined by the characteristics of that gas, but by the quantity of the gas in moles. Number 9, a liquid's temperature is lowered from 50 degrees Celsius to 10 degrees Celsius, so we're cooling it. Did the liquid's vapor pressure increase, decrease, or stay the same? Now just think back to chart 11.2, or table 11.2, right? That deals with water. That's a liquid. Water is not the exception here. It acts like every other liquid. So as you take something, you cool it, what does the vapor pressure do? What happens to the vapor pressure? I think yesterday we talked about warming it, right? As we warm it, as we have this container of liquid, and we have a molecule that breaks free. And the more that break free, the more that sit on the top, the more pressure they create. Think of it that way. Okay, that's one way to think about it. So as we heat it up, the vapor pressure increases until we get to the boiling point, which is where the vapor pressure equals the atmospheric pressure. Okay? So if we go the other way, if we cool it, what happens? Does the vapor pressure increase or decrease? It increases when we increase the temperature. So as we decrease the temperature, we decrease the vapor pressure. Right? And if you looked at that chart, just follow it up and down, you know. As you increase the temperature, the vapor pressure increases, and it keeps increasing until it reaches atmospheric pressure. Okay. Any questions on those review questions? three characteristics of an ideal gas. It operates ideally at or around standard temperature pressure. What standard temperature and pressure are, be able to identify them. The pressure of a gas is based upon the amount of that gas, not based upon the characteristics, individual personal characteristics of that gas. And that vapor pressure increases as you increase temperature and decreases as you decrease temperature. Those are the big teaching points there. Practice problem 4. In an experiment similar to experiment 8.1, don't worry about that, a chemist collects carbon dioxide over water. Okay, so now we're going to be doing one of those experiments. The chemist is collecting carbon dioxide over water. So we've got the flask here, comes in, blip, blip, blip. We're collecting carbon dioxide over water.
Aren't you so proud of me?
Not the first word I thought of. You need help?
Oh, no, I'm fine, I'm fine.
Look at Aaron's making it look
I'm a
easy.
strong, independent woman.
Man up, Sydney. Let's go.
I made it up.
Aaron and Mr. Parker are putting you to shame. Come on, man up. All right, so collecting carbon dioxide over water. This is what's happening. Okay. It's over water, temperature is 24 degrees Celsius. That's it. 24 degrees Celsius there. If the gas in the collection vessel has a pressure of 790 torr, let's pretend that this collection vessel here has a meter on it. 790 torr. So that inside this container, 790 torr. Okay. What's the pressure of the carbon dioxide in the vessel? What's the pressure of the carbon dioxide inside the vessel? Now if we take that collection vessel and magnify it up right here, here's the top of that vessel. And let's say that here is the liquid level. What's the pressure inside this space? Hopefully now you realize that there are two different pressures within this space, not just one single pressure. The single pressure, the total pressure of the space is 790 torr, right? The gauge that's reading the total pressure is 790 torr. That 790 torr is made up of two different partial pressures. If we think of it as there is a pressure band in that area, but there's also a pressure band in that area. That area right there, the larger collection area, that is your CO2. Here, I'll use an arrow because it stinks. Okay, there's your CO2. What pressure band is right in here? There we go. We'll get some real marker going. You've got CO2 in that space, but you also have the vapor pressure of the water. So this is the pressure of the CO2. This is the pressure of the H2O. The total pressure in the space is 790. So using Dalton's law of partial pressures, the pressure total is equal to P1 plus P2 plus however many partial pressures we have. Pressure total is 790. That pressure equals pressure of the CO2 plus pressure of the H2O. We were asked to solve for what is the pressure of the carbon dioxide. In order to solve for that, I need to know the pressure of the water. The pressure of the water is your vapor pressure for the water. So where do I get this number from? flip back to table 11.2. Table 11.2, temperature is at 24 degrees. And what does the chart tell me the vapor pressure of water is at 24 degrees? If you have a book, please turn to page 397. Practice looking at the table if you didn't already. And the vapor pressure at 24 degrees is 22.4 torr. Just happens to rhyme. Okay? 22.4 torr. So 790 torr equals the pressure of the CO2 plus 22.4. That's all in torr, so I dropped the units. We're talking torr now. So I've got torr equals pressure plus pressure in torr. Subtract 22.4 from both sides. Pressure of the CO2, 767.6. Now, how precise can I be? I'm doing addition, right? So my issue here is precision. Addition and subtraction, I can only be as precise as the least precise. I've got 790 torr. It's precise to the ones place. My pressure is precise to the tenths place, but my answer can only go to the ones place because this is the least precise, and so it is 768 torr. Okay. In this space, there are 790 torr of pressure. That 790 torr of pressure comes from 22.4 torr of pressure from the vapor pressure of the water in which the gas is being collected. Remember, it's going bloop, 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 in water. So I've got the vapor pressure of the water, and I've got the pressure of the gas that's been collected over that water. Now, it may not seem like a big deal now. You might just think in terms of, hey, all I need to really know is a 790 torr. Not so much. That's why we're trying to push a little bit forward in the lectures to get us into this concept of, okay, now that I recognize that I actually have 768 torr of carbon dioxide, there are some things that I can learn about the carbon dioxide. Because this has probably happened as a result of a reaction, and we're going to start to describe that reaction based upon the product of reaction in the carbon dioxide. So before we can get over to talk about this reaction, we need to more fully understand the results of the reaction. Lastly, we asked you to do EPP number 4. Before we go there, either any more questions? Hopefully this answered questions you had on the problem if you didn't get it. Any other? We're good? A little bit of bobble from everybody, just a little motion? Okay, we're moving on. Some of you still look like you're in traction, but we'll move on anyway. If I say yes, he'll think I understand it, and I don't. But if I say no, he'll stop and we'll do some more, and I don't want to do that either. So what am I going to do? I'll just not move. EPP number 4. A mixture of nitrogen and oxygen is stored at a temperature of 25 degrees Celsius, pressure of 2 atmospheres. And if the partial pressure of the nitrogen in the mix is 1.4 atmospheres, what's the partial pressure of the oxygen in the mix? Pressure total equal pressure 1 plus pressure 2 plus however many other partial pressures I have. Okay, the mixture, what is the total pressure of the mixture according to the problem? Let me read it again. A mixture of nitrogen and oxygen is stored at a temperature of 25 degrees Celsius and a pressure of 2 atmospheres. So total pressure is 2.0 atmospheres. And that's going to equal the partial pressures within that space. We're not collecting over water, so we don't have to worry about vapor pressure, right? They're just, the gases are in container. And it says the partial pressure of nitrogen is 1.4 atmospheres. What's the partial pressure of oxygen? What is 2 minus 1.4? 0.6. Yeah. 0.6. Any questions? That's it. 0.6 atmospheres. That's it. That's all. If you could subtract 1.4 from 2.0, you can do chemistry. See how simple that is? Mind blown, huh? Oh, I guess I'm supposed to go. That's the thing now. Or at least it was the thing, at least yesterday, so I don't know what it is today. Let's go ahead and press on with, well, we don't get into PV equals nRT quite yet. An alternative statement of Dalton's law. Page 399 is where we're at. Let's go ahead and pick up with the alternative statement of Dalton's law. I'm going to go ahead and leave that on the board because that is Dalton's law, right? Dalton's law of partial pressures. To repeat, the total pressure in a space of a mixture of gases, the total pressure that you're experiencing there is equal to the sum of all the partial pressures in that space. So in the last problem, it was 1.4 atmospheres of nitrogen and 0.6 atmospheres of oxygen. You bring those two pressures together, and the resulting pressure of the whole thing is not the average of those two, it is the sum of those two. That's what people tend to think a lot of times. If I bring a 1.4 atmosphere and a 0.6 together, what you bring them together and say, what do they average out to be? That's not what you're thinking. You're thinking, okay, I bring this pressure in, and I bring another pressure in. They add together to form the total pressure. They add together. That's what Dalton's law is telling you. The total pressure is equal to the sums of the partial pressures. The partial pressure just means one piece of the mix, another piece of the mix, a third piece of the mix. You could have 7, 8, 10, 12 gases mixed together. If you knew the pressure of every one of them that was added together, of every one that was brought into that mix, and you added them together, you would have the total pressure in that space. That's what Dalton's law is telling us. Now, if you look on 399, they introduce you to equation 1110, which is going to be this multiple. The mole fraction is what we're calling it, is what it is. It's the mole fraction. Let's say in the last example, we had the total pressure was equal to the pressure of the nitrogen plus the pressure of the oxygen. Okay? Now, we said before that the pressure of gases is not based upon the characteristics of the individual gas. It's based upon the amount of that gas in moles that's in that space. Okay? So it's not about carbon dioxide and nitrogen when they get together, that there's something unique about nitrogen that it contributes a certain pressure, and unique about oxygen that makes it contribute a certain pressure. It's a fact of, hey, if I have 3 moles of nitrogen and 1 mole of oxygen, the nitrogen, hopefully you see, is contributing a larger portion of the total pressure because we've got more of it in the same space. This idea of a mole fraction, all this means is of the total number of moles that I have that I'm assessing, the total number of moles, how much of that comes from each one of the partial components. Let's go ahead and use nitrogen and oxygen. Let's say we're looking at a mixture that has a total pressure, that I have a pressure of nitrogen and a pressure of oxygen in that space. And if I were to come back and tell you that, oh, I have 2 moles of nitrogen and I have 3 moles of oxygen. Okay? How many moles of gas do I have? If I have a nitrogen-oxygen mix, and I mix 2 moles of nitrogen and 3 moles of oxygen, how many moles of gas do I have? Well, much like the last problem, it's really hard. We have 5 moles of the mixture, right? They're not reacting to each other. The oxygen and nitrogen here aren't reacting. They're coexisting. Oxygen's in its homonuclear diatomic, nitrogen's homonuclear diatomic. They don't want to break up. They're going to be in the blend. They're not going to be forming NO, NO2. They're not going to be reacting. They're going to be in the same space as part of a homogeneous mixture of gases. And so if I have 2 moles of one and 3 moles of the other, hopefully you would see that in that space I've got 5 moles of gas. 5 moles in that mixture. Now if I said to you, what percentage of the moles in that mixture are nitrogen? What percentage? What would you do? How would you figure that out? If 2 moles are nitrogen and 3 moles are oxygen, what percentage of that mixture is nitrogen? Pardon, Seth? 2/5, right? Because I have 2 moles of nitrogen. Of the total, I have 2/5 of the total mixture is nitrogen, 40%. Because 2 over 5 is the same as 4 over 10, which is the same as 40 over 100, that's 40%. Okay? What's the percentage of oxygen? It's going to be 3/5, or 60%. 3 over 5 is 6 over 10 is 60 over 100, 60%. So in that mixture, I say, okay, 40% is nitrogen and 60% is oxygen. Are we good with that? Okay. Now if I go back and say the pressure in the space is a result of the pressures of the individual gases and their quantity of those gases, not the characteristics of the gas. Let's go back and look at this. The total pressure. What percent of the pressure do you think in this mix is coming from nitrogen? Okay, I've got a space that I have a gas mixture in it. We've said that the pressure comes from the amount, not the identity of the gas. Okay, I have a certain amount of pressure in that space. 40% or 2/5 of that gas is nitrogen. How much of the pressure is coming from nitrogen? 2/5. I have 60% of that space has oxygen. 60% of the gas that I have in this space is oxygen. How much of the total pressure is coming from the oxygen? 60%. Okay. So what this turns out then to be is that the total pressure, you might say, we would agree, is the pressure of the nitrogen and the pressure of the oxygen in the space. That's the way we've looked at Dalton's law of partial pressures up until this point. That the total pressure is equal to the pressure of each of the parts. But if I don't know the pressure of each of the parts, all I know is how much of each I have. How do I figure out the pressure that contributes? And it's using this partial pressure, this mole fraction. The mole fraction is the number of moles of the part over the number of moles of the whole. In that last example I had written up there, how many moles of nitrogen? 2. How many moles total? 5. My fraction there then would be, if for nitrogen it was 2 over 5, then my x is going to be equal to 0.4. See that? And in the case of the oxygen, we had 3/5, which is going to be equal to 0.6. So if I know how much of each gas, I can figure out the pressure it contributes. And conversely, later on, if I know how much pressure it contributes, I can figure out how much of it is there in proportion to the others. That's the key we're going to be working on using this alternative statement of partial pressure. Here's what it looks like in the total. The pressure total equals the pressure from the nitrogen and the pressure from the oxygen. Another way to say that is the total pressure is equal to the mole fraction of nitrogen times the total pressure and the mole fraction of oxygen times the total pressure. Putting it another way, using this example of nitrogen and oxygen, I could say that the total pressure in that space, the part that comes from nitrogen is 0.4 times the total pressure, and the part that comes from oxygen is 0.6 times the total pressure. 0.4 and 0.6 is 1. Total pressure equals total pressure. Where does that total pressure come from? Partials. How do I figure out this mole fraction? It's the proportion of the amount of that gas as a part of the whole. If 2/5 of the gas by mole count is a particular gas, then 40% of the pressure comes from that gas. So, again, I'll just write it again in summary. Dalton's law of partial pressure says that the pressure total is equal to pressure of each of the parts added together, however many they are. The mole fraction, X, is equal to the number of moles of the gas over the number of moles of the mixture. Okay, that's another way of saying that. Moles of that gas over moles of the mixture. The alternative way of writing Dalton's law is that the total pressure is equal to the mole fraction of 1 times the total pressure plus the mole fraction of the second times the total pressure for as many parts as there are. Okay? Now some of you are really scared because that's X. It's English. I'm not good at English. Okay, I can see it in your eyes right now. Please, what is the difficult part of this? Is the hardest part understanding that the pressure in the volume is equal to the partial pressures of all the gases in the volume? Is that difficult to understand? Any feedback? Yes, no? Is that hard to understand? Okay. General consensus is no. So no or no opinion. Do you believe it's difficult to understand? Okay. That the total pressure in a space is equal to the sum of the pressures in the space. Okay? So, I mean, let's just break it down to the concept. That's the first concept. The second concept is the percentage of a gas in the space. How much nitrogen there is, how much oxygen there is. You know, we have the air we're breathing, it's what, 78% nitrogen? Does it bother you that you're breathing nitrogen right now? And one thing we know about nitrogen, remember from our unit on that, is it's inert, so you're breathing it in, and guess what? You're breathing it out. It's going in and out, and it doesn't react with you. It's inert. What's nitrogen do? It reduces the concentration of the oxygen to a level where you breathe it and you have enough oxygen to live, but not so much oxygen that you hyperventilate. And not so little oxygen that you pass out and become hypoxic. So God makes this mixture that provides enough inert material to dilute down the oxygen to be right at the perfect range for you to live. Okay? But hopefully you understand the gas in this room right now is a mixture of oxygen, nitrogen, carbon dioxide, ozone. I mean, lots of different gases. And the total pressure that you're feeling is the sum of all the partial pressures of all of those individual gases. That's one way to think about it. If I have a room that has 2% nitrogen in the room, how much of the pressure in the room is coming from the nitrogen? 2%. Suddenly there's 50% in the room. 50% of the gas in the room is nitrogen. How much of the pressure in the room is coming from nitrogen? 50%. So whatever percentage by mole, not by volume, by mole count, how many molecules are in that space? If 40% of the molecules in that space come from one gas, then that gas is contributing 40% of the total pressure of that gas. So we're dealing with addition and division and multiplication. There's no integration, no differential equations. Again, so think back, when did we learn addition? Have you had that for at least a couple years? You feel comfortable with addition? Like that 2.0 minus 1.6, did that, or 1.4, did that really throw anybody? Mr. Baker, how did you do that? Well, I counted up 1, 2, 3, 4, 5, 6, and I took these many away. You know, okay, so it's not the addition and subtraction that's bugging you. Does anybody here have a problem multiplying? Like 0.4 times something plus 0.3 times that same thing equals 0.7 times that thing? No? Okay. Division. Yes, sir. Okay. Welcome back. Okay, any other? So, that's the core of Dalton's law. Let's see if we've even finished the entire content from that. Let's look at a problem then. We've got time to look at one of the examples, and hopefully by example, something will click. If you look at the top of page 400. Yep. Yeah, get the moisture in, get the moisture out. Let's go.
Mr. Baker, it's an hour class. That's a long time. I can't hold it that long. My throat is so parched.
See, you getting your drink, it's made me thirsty. Right. I need my caffeine, helps me cope. Gives me energy. All right. Let's look at example 11.3. It actually starts at the bottom of 399 then. Okay. We're going to apply the alternative statement of Dalton's partial pressures. A mixture of gas contains 3 moles of O2 gas, 5 moles of nitrogen gas, and 1 mole of neon. What's the mole fraction of each component of the mixture? Mole fraction for each one of them is the number of moles of the gas divided by the number of moles in the mixture, right? So, how many moles are in the mixture? There are 9. So, the partial pressure of O2, or excuse me, yeah, the mole fraction of O2 is what? 3/9. The mole fraction of N2 is equal to, and the mole fraction for neon is equal to, okay? Is anybody troubled about that? You're going to be able to sleep tonight. Okay, that's it. Yeah. Oh, you're forcing me to learn. No, I'm not. It hurts, Mr. Baker. Okay, good, you're learning. Here we go. You're not learning if it doesn't hurt. Oh, let's go ahead and extend this. Actually, no. Let's not extend it. Let's go on to example 11.4. Because let's apply it. Because I could take this one and work a hypothetical problem, but 11.4 is an actual problem, so you can see the work in front of you. We can go over it together. You can follow it on the page. You can put it in your notes. It's all good. Here we go. I know, that was painful. That was 11.4. Here we go. A gas mixture contains 40 grams of carbon. Yes? Don't tell me you don't understand that. No, go ahead. Well, if you noticed in the book, they put them in decimal form. I just left them as fractional up there. But on here, they 0.33, 0.56, and 0.11. You would, no, you'd use them as decimal form because in a minute you're going to use those in an equation and you'll need them in decimal form. We go to next year's no talking in the hall policy, you'll know why. How'd that be? No talking in the hall. It's not quite as bad as no breathing in the hall. Like, okay, ready? And and run out the door.
Are you really gonna do that?
I'm just starting the rumors. I love hearing the rumors about me all the time, so I figured I'd start another one. You hear Mr. Baker's going to start a no talking in the hall policy?
You should.
Just go ahead and, well, I don't have to tell you. You'll tell your class, of the other students anyway.
Just go to school on Friday, on Good Friday.
Pardon?
You didn't hear about that? Oh my. So I was doing announcements on,
Oh, yeah, I heard that. I didn't think that was a joke.
you didn't think it was a joke?
No.
You thought I meant
I sat there and listened for myself to chuckle and went, no, didn't even, no.
I was trying to trick everybody.
Yeah.
You got two people.
I'm mean like that, yeah. You know what? Good Friday is canceled. The guy in the building that has probably the most respect for church history just decided we're going to come to school on Good Friday anyway. No, it's not going to happen. We had a day off that the public school didn't. I didn't get any grief for that. I got grief for the day we did have school and the public school didn't, but I didn't grief when we didn't have school when they did. Imagine that. The day when we did have school and everybody else took a snow day, and I had all those parents say, well, from now on, you need to tell us every day when we do have school. And I said, no, we're not playing that game. No, I'll let you know we're not, otherwise we are. I'll institute that policy the same day I institute the no breathing in the hallway policy, okay? Here we go. Let's go back to example 11.4.
No school tomorrow. That's the rumor.
It's more likely we'll have school on Saturday than that we won't have school tomorrow. Just saying. Well, I'll almost guarantee you'll have Sundays off next year. Here we go. A gas mixture contains 40 grams of carbon. Hey, we should link the days of school to your tests, like your standardized testing. Sorry, turnover's really low. We're going to 6 days a week. That's a great rumor. Feel free to start that one. Oh, next week's testing. If we do really poorly, they said next year we're going to come to school on Saturdays too. No, right now Saturdays is just for detention. That's the only thing we have planned for Saturdays right now. All right, I'm having way too much fun here. Let's go on to example 11.4. Austin, pull it in. Woo, here we go. A gas mixture contains 40 grams of carbon monoxide. Okay. 40 grams of carbon monoxide, 10 grams of nitrogen dioxide. Is it monoxide or dioxide? Carbon monoxide, nitrogen dioxide. Okay. If the total pressure of the gas is 1.2 atmospheres, what's the partial pressure of each gas? Of that 1.2 atmospheres, how much of that pressure is coming from the carbon monoxide and how much of that pressure is coming from the nitrogen dioxide? Okay. So far, the only way we know how to do this would be that the total pressure is equal to the mole fraction of the carbon monoxide times the total pressure and the mole fraction of the nitrogen dioxide and times the total pressure, right? So I need to come up with the mole fractions for carbon monoxide and nitrogen dioxide. So, to come up with a mole fraction, Austin, what do I need to do? The standard formula for mole fraction is the number of moles of the gas divided by the total number of moles in the mixture. Okay? So I need to know how many moles of carbon monoxide I have. Yes, sir. Okay. Never mind. Okay. So, carbon monoxide. How many moles do I have? I don't know yet, but I can compute it really quickly, can't I? Yes, sir. Well, I've got grams, and I'm trying to go to moles. So with my solution diagram, if you imagine that, you're going down to get moles, right? So I'm doing something with the molar mass, and I'm going down, so I'm dividing. So mass divided by the molar mass will give me the number of moles. You see in your text, 28 grams per mole. That lets me know 40 grams, another way to say that. 40 grams divided by 28 grams per mole is going to give me 1.43 moles. So I've got 1.43 moles of carbon monoxide. Moles of of nitrogen dioxide. Well, imagine that. It's 28 grams again. Same mass. Is that right? I don't trust the book, by the way. That's why I'm doing this. Carbon monoxide, 12 and 16. Right? 12, 16 is 28. That works. Nitrogen dioxide, (14 and 32 is not 28. What does your book say? On page 401, second line of the math.
46.0.
Divided by 46.0. See, I've got first printing. I don't trust it. So this is 46.0. So I've got 10 grams divided by 46.0 grams per mole. And that equals how much? 0.217. So 0.217 moles. See, that's the answer is right. My book has 10 divided by 28 is 2.2. I looked at it and said, that's wrong. Right? 10 by 28 is a little bit less than a third, not 20%. All right, so I have 1.43 moles of CO, and I've got 0.217 moles of NO2. How many moles do I have in the mixture? Well, 1.43 plus 0.217. Right? That's 1.65. That's what the book says. So my total number of moles, my mole fraction is going to be the number of moles of the gas, of each gas, divided by the number of moles total in the mixture. Number of moles total in the mixture is 1.65 moles. Easy for me to say, right? 1.65 moles. Now I need for each of the gases, for the carbon monoxide and the nitrogen dioxide, I need to come up with the mole fraction. If I have 1.65 moles total, what's my mole fraction for carbon monoxide? It's going to be 1.43 divided by 1.65. Because of the total of 1.65 moles, 1.43 of those come from carbon monoxide. So my mole fraction for carbon monoxide is equal to 1.43 divided by 1.65. That comes out to be 0.867. What does this tell me? Just in plain math. You guys done? Okay? I don't know. I just look up, you guys are kind of looking at each other and smiling, and I just assume you guys are carrying on a conversation. Just making sure you're done before I keep going. Okay, good. Glad to hear it. So, 1.43, in just plain speak, or sign language, or whatever you use behind my back. Okay? 1.43 divided by 1.67. It tells me that 86.7% of the molecules in that mixture come from carbon monoxide. 86.7%. So guess what? This gas is going to contribute 86.7% of the pressure as well. And the mole fraction of NO2, number of moles is 0.217. Okay. Divided by 1.65 total, it comes out to be 0.132. 13.2% of the total mixture is nitrogen dioxide. So if 86.7% of it is carbon monoxide, 86.7% of the pressure comes from carbon monoxide. And if 13.2% of the total number of moles comes from nitrogen dioxide, then 13.2% of the total pressure comes from the nitrogen dioxide. All right, epiphany, good. So the total pressure is equal to the mole fraction of carbon monoxide times the total pressure plus the mole fraction of the NO2 times the total pressure. If the total pressure in this case is 1.2 atmospheres, the pressure that comes from the carbon monoxide, this part right here, is going to be 0.867 times the total pressure, which was 1.2 atmospheres. When I do that math, this will tell me how much of that pressure is carbon monoxide in atmospheres. And in the same way, the pressure of the NO2 is equal to the mole fraction of the NO2 plus the total pressure, which is going to be equal to 0.217 times 1.2. So my pressure for the nitrogen is the mole fraction times the total pressure. Pressure of carbon monoxide is the mole fraction times the total pressure. And when you add these together, 86.7% of 1.2 and 13.2% of 1.2, guess what it comes out to be? 1.2.